Chris White, who will talk about the classical double copy.
Great. Well, thanks for to the organisers for the invitation to speak here. This is work done with my student, Andres Luna, Douglas O'Connell, Ricardo Montero, and Izzy Nicholson. So, to give an overview of the talk, I'll give a brief introduction to BCJ duality and the double copy, really just to introduce the notation I need. We've also seen this in some of the other talks today. I'll then talk about the classical double copy, which is a map between exact solutions in gauge theories and gravity theories. And in particular, I'll talk about things called stationary Kerr-Schild metrics, which is a kind of infinite family of exact solutions where we know how to do this classical double copy. I'll then talk about recent attempts we've done to try and go beyond that simplest picture. And then I'll end by talking about non-perturbative solutions in biaxial theories, and I'll try and justify why as we go along. And then I'll conclude with an outlook and some open questions and so on. So this is an Amplitudes conference, so let me start by writing an amplitude, which we all know and love. So this is the general form of an endpoint L-loop amplitude in non-abelian gauge theory. I can write this as powers of the coupling constant, sums over cubic graphs, or the integrals over loop momenta, symmetry factors, and so on. Also these denominator factors, which for example may come from propagators. And also, if it's a non-abelian theory, we'll have some colour factors for each of those graphs. And n here, what we call the kinematic numerator, is everything else. So this depends on polarisation vectors and momenta and so on. Now for those that haven't seen this form before, you may ask, why am I only summing over cubic topologies, whereas in Yang-Mills theory, for example, we have a quartic vertex. The point is I can always choose to write those multiple interaction vertices as sums of products of cubic vertices so that the amplitude assumes this form. Now these kinematic numerators, of course, are not unique. They are gauge dependent, and also there is a generalized gauge freedom which we can use to put those in a different form. Now there's an interesting recent conjecture which has now become known as BCJ duality. It says that you can choose these kinematic numerators to obey similar Jacobi identities to the colour factors. So always when I have some graphs, I can arrange them into overlapping sets of three whose colour factors obey the Jacobi identities associated with the structure constants coming from the colour algebra. What this conjecture says, this BCJ duality, is that I can choose the numerators so they obey similar Jacobi identities as functions of their momenta. And that then is also referred to as colour kinematics duality, because it hints at some structure or some similarly algebra that's underlying the kinematic factors that somehow mirrors what's going on in the colour sector. Anyway, that is an amplitude in non-abelian gauge theory. There's then something called the double copy conjecture, which states that if I've written a gauge theory amplitude in BCJ dual form, then this quantity here is an endpoint L-loop gravity amplitude now, rather than a Yang-Mills amplitude or gauge theory amplitude. Now to obtain this expression, all that's happened is that this gauge theory coupling constant has been replaced with a gravitational coupling constant, and also the colour factors have been stripped off because there is no colour in gravity, and replaced with a second set of kinematic numerators. And there's a tilde on those because they don't have to come from the same gauge theory, so I can take two different gauge theories and bolt them together, and that would give me a different gravity theory in general. So which gravity theory you get, with or without supersymmetry, for example, depends on which gauge theories you start with. Well, that's one way to go. Now I could have also started with this expression, stripped off the numerators, and put on a second set of colour factors. So that would give me this amplitude here, where I have just relabeled the coupling constant to be some other coupling constant of y. And you can then ask, what kind of theory is that an amplitude in? And the answer is something called a biadjoint scalar theory. So because this has two different kinds of colour factor, the field will have two different kinds of colour index, which is what this A and A prime are. But it's a scalar field because there's just a sort of trivial kinematic dependence in the numerator. And the full field equation of this, well, it has an interaction term here, so this nonlinear term, which involves manifestly a product of structure constants, where those are different structure constants, so they're in the two different the algebras representing these different kinds of colour charge, if you like. So that would come from a cubic term from the Lagrangian, so this is a cubic theory. And these theories have started to crop up all over the place. So they crop up in this double copy story, or this zeroth copy story, They also occur in the discussion of the CHY equations, for example. So they're popping up in lots of different places. Now, one of the uses of these theories, or one of the reasons they're interesting, is that BCJ duality is actually manifest in this theory. The cubic Feynman rule involves a product of two structure constants. So every time you have a Jacobi identity for one set of structure constants, you'll also have one for the other, because every diagram at every vertex will involve a product of these two things. Now that means that amplitudes in this biadjoint theory can play the role of building blocks for kinematic numerators in gauge theories, and in fact they have done. They have been used for that purpose. There's a paper by these people here. So in some sense, the properties of biadjoint theories somehow underlie the properties of gauge theories in gravity. So you have this full ladder of theories from biadjoint to gauge theory to gravity, and these ones at the bottom are somehow passing on their information to other theories. Now, I've already talked about those three particular types of theory here. Much more general theories are possible, as we've also been hearing about at this conference, but also obey double copy-like structures. So what is the double copy actually good for? Why do we care about it? Well, I've listed here some potential applications of the double copy that I can think of, but I'm sure people here can think of others as well. One of the uses that has been investigated already is investigating possible quantum gravity theories. So, for example, is NSH supergravity ultraviolet finite or not? You can take amplitudes in NS4 super young mills, run them through the double copy, and investigate NSH supergravity. You can do the same for other gravity theories. Something else it can be useful for is simplifying amplitude calculations in gauge and gravity theories. BCJ duality, in particular, is a new structure, and usually when you make structure manifest in an amplitude, it gives you extra constraints if you're making an ansatz or something, and can simplify calculations. So that's another hope of what this might be useful for. Two perhaps more speculative but quite optimistic applications would be, first of all, it could give you a new way to calculate perturbations in general relativity, things like gravitational waves. So there may be an application to kind of astro-pH type physics. Also, a new way to calculate cosmological perturbations. So we have some evidence from the work that we've been doing that says that this double copy may work on curved space. And if we take de Sitter, then you're basically calculating cosmological perturbations, so that could be in principle of use. This body of work is also useful for probing the relationship between string and field theories and how those all tie in together. And finally, another thing I could think of was that you could use this to generate new perturbative or non-perturbative solutions in Yang-Mills theory and or gravity. So you can show that things are related in these two theories, and if you have a solution in one of those theories, it may give you some insight into solutions in another. That famous book of exact solutions of Einstein's field equations that gets gradually thicker over the years could be enhanced perhaps by these ideas. Now, to this end, we need to know actually whether we can trust the double copy. So I've talked about this thing as if it's true. Is it? Well, there is a mounting sort of body of evidence that this thing is actually true. So at tree level, it's known to be equivalent to the KLT relations in string theory. It's been tested very impressively up to 4-loop order in NS4 super Yang-Mills. There's also been a lot of fixed order amplitudes calculated in other theories, including completely non-supersymmetric theories. And I'm afraid I haven't put a list of authors there because it would just be very long. It also works for form factors as well as amplitudes. And then there are certain kinematic limits of amplitudes where we actually know the structure to all orders in perturbation theory. So, for example, in the soft limit, or the Reggie limit, which is where the centre of mass energy is much bigger than the momentum transfer, we know the structure of the amplitude to all orders in that limit, and we know that the double copy matches up and works out. There's also a nice realisation of both BCJ duality and the double copy in the self-dual sector. So you can write equations if you project out one of the degrees of freedom of the gauge field and insist, in other words, that it be self-dual. You can write equations for the gauge theory and the gravity theory that look extremely similar to each other, and you can then even get an interpretation of what this kinematically algebra is that's underlying BCJ duality. And that, unfortunately, doesn't generalise to the full theory, but it's a very nice set of ideas. And finally, there's some loop-level insight coming increasingly from ambi-twistor string theory, and that ties into the CHY equations, but of course that also has something to say about the double copy. So the double copy suggests, if it's true, a very profound link between gauge and gravity theories. These are two completely different theories with very different applications in terms of what they're useful for and what experiments they can be tested in. So the fact those two are related is very nice indeed. However, all of the statements of the double copy up to now are purely perturbative. So it's been defined, as I wrote down, for perturbative amplitudes. And there's no, as yet, all-order Lagrangian understanding or non-perturbative understanding of where this thing might be coming from. Now, if a deeper connection indeed exists between these two types of theory, then it must be possible to take exact solutions in both theories, so things that are not fixed-order perturbative expressions, and to show that those actually match up as well. And then that's more evidence of the double copy being correct, but also opens up more uses for the double copy. So the basic idea of what we're trying to do is as follows. Step one is to try and find a gauge field living in a gauge theory and a graviton living obviously in a gravity theory, such that the graviton is some kind of product of gauge fields. So I've written that very schematically here. And when I say graviton, I could also mean a two-forward a dilaton and the other fields that you expect to be there under the double copy. But that's basically what we mean by having a double copy, very schematically. And the second step is that we want to show that that is actually related to the BCJ double copy for amplitudes. So we want to show that whatever we achieve here is actually the same thing that's underlying amplitudes that I talked about just now. But in fact, we have so far found an infinite class of fields that indeed obey both of these things. So that goes back to a paper a couple of years ago with my collaborators. And our starting point was to consider things called Kerr-Schild metrics in general relativity. Now, I don't expect everyone will have seen these before, so I'll give a quick summary of what they involve. First of all, I'll define the graviton as usual as the deviation from Minkowski space. You can also define Kerr-Schild metrics around some non-Minkowski background, but I won't talk about that in this talk. And these Kerr-Schild metrics have the very special property that the graviton field can be written as some scalar function times an outer product of some vector k with itself. And that can't be any odd vector, that has to be a null vector, and it also has to be geodetic, which is this condition here. Now, I'll only be worrying about the graviton in the double copy here, so for the experts you would expect a dilaton and a two-form potentially on the gravity side, but because this thing is, this vector is null, the trace of this vanishes and so there's no dilaton. Also, this copy is manifestly symmetric, so I don't have to worry about any anti-symmetric part. Now, the reason these Kerr-Schild metrics are very nice is because they turn out to completely linearize the Einstein equations. So, for example, if I plug them in to the Ricci tensor and I put one index up and one index down, and one indeed has to do that particular index placement, then you get this expression here, which is indeed linear in these various quantities. Now, why is that important? Well, I said we wanted to match up exact solutions in both theories, and the fact that this is now a solution of the linear equation tells us that such solutions are exact and that there are no higher order perturbative corrections. So that's a good starting point to try and construct an exact classical double copy. Well, how are we going to take the double copy? Well, I'll start with the graviton, so actually we want to take the single copy back into a gauge field. The form of this result, which has an outer product of this vector, does suggest how I might form a single copy gauge field. I could, for example, try just getting rid of one of these vectors to give me something with only one Lorentz index, and then if I want to embed this in a non-abelian theory, I'll put some arbitrary colour vector here, which is just what this CA is. Now, what we were able to prove is that for all stationary solutions, so those not depending explicitly on the time, this gauge field thus defined from these Kerr-Schild metrics solves the linearized Yang-Mills equations. So in other words, these equations here, where this is the field strength tensor that one would get in a abelian theory rather than a non-abelian one. Now, it's perhaps not surprising that this thing satisfies the linear equations, because we started with something on the gravity side that also linearized the field equations. But what this tells us anyway, at least in principle, is that every stationary Kerr-Schild graviton has a well-defined gauge theory single copy. So this field is a proper gauge field, meaning that it satisfies the Yang-Mills equations. However, if you've been watching carefully, you'll know that that single copy procedure I just described is ambiguous. So I took off one of these vectors here, but I could have, for example, absorbed some amount of this function into the vectors before I did that. So there was kind of an ambiguity there, and if I had made other choices, I wouldn't have satisfied, in fact, these equations. So one can ask, what actually is it that fixes what this phi has to be, meaning that function that you don't square or you don't touch when you take the double copy? But in fact, it turns out to be fixed by the zeroth copy, which is why I wanted to mention the zeroth copy earlier on in the talk. If I go a step further and take the 0th copy, it means getting rid of this vector as well, and also having a second arbitrary colour vector, so I'll get something with 2 adjoint indices. And you can then show that phi must be a solution of the linearized biadjoint equation. So I wrote the biadjoint equation earlier, it had a non-linear term, that actually vanishes when you put this in, and you end up with this equation here. Now there's another way to think about that, which is that phi itself is just a scalar propagator. That's the interpretation of that equation. So indeed this is exactly the same as the BCJ procedure for amplitudes. The BCJ double copy, you touch the numerators of the amplitudes, so you strip off the colour factors and you put in more kinematic numerators, but you don't touch the denominators at all, and those denominators have the interpretation, of course, as scalar propagators. So that's exactly the same thing as what's going on here. So that was quite an abstract discussion. So let me now give a couple of examples. And let's start with perhaps our favourite black hole, which is the Schwarzschild black hole. We can ask from this double copy procedure, what, if you like, is the square root of a Schwarzschild black hole? So the thing that when you double copy it, gives you the Schwarzschild black hole. What's important here is that indeed the Schwarzschild solution has a Kerr-Schild form, and it turns out in that case that phi, this Kerr-Schild field, goes like 1 over r, and the Kerr-Schild vector Ku just has 1 in the time-like direction, and it's the unit radial vector in the space-like bit. So using the rules that I've just given you, I can take the Kerr-Schild single copy, which means that I take only 1 copy of this vector, but then keep the field phi intact. I've also changed some coupling constants over, as I'll say in a minute, and put in an arbitrary amount of colour charge. And we don't necessarily recognise this gauge field here, but if you gauge transform it, it's quite a simple gauge transformation, takes you to this form. And this certainly is recognisable because this is just the gauge field of a point charge. So the square root, if you like, of a Schwarzschild black hole is just a point charge at the origin. Now that's itself quite an interesting result because naively one might expect that some complicated non-abelian object copies to give you a Schwarzschild black hole, and that's what we thought would happen for quite a while before we actually found this result. So if you write down the Schwarzschild metric in most gauges, it goes to all orders in the gravitational coupling, so you'd think you would have to have some horribly non-linear thing in the Yang-Mills theory, which would then copy term by term to give you, in the coupling that is, to give you the Schwarzschild result. Here it's saying that actually things are much simpler than that, so thought about in the right way, you can actually just take an abelian solution and that will map to the Schwarzschild black hole. Now that's not to say that there's also a non-abelian thing that would map to the same thing, and that's because information gets lost when you do the double copy. So you strip off the colour factors, for example. But it does mean if you had some non-linear object in the gauge theory, you could presumably just gauge away that complication to leave you with an abelian-like result. The other thing we can note is that this phi field is 1 over r, so that is indeed a scalar propagator, and that's what we expect, consistent with that interpretation of the 0th copy that I was talking about. And the other thing is that if I want to recognise this as a Coulomb solution, meaning I really want the 4 pi here, and I want that to be the charge and that to be the coupling and so on, then all the factors of 2, etc. work out precisely according to the usual BCJ description. So for example, the coupling constant of the gauge theory gets replaced with the kappa over 2, which is what happens in the amplitude story. And also the equivalent of replacing colour factors with kinematic numerators is that a static charge becomes, if you like, a static Form momentum, or a mass. The other thing I'll just say as an aside is this works in any number of dimensions, where strictly speaking it's a Tangolini black hole rather than a Schwarzschild one. But it must work in arbitrary numbers of dimensions if this is the same as the story for amplitudes, because that also doesn't depend on the number of dimensions. A second example I can give is the Kerr black hole, which is another well-known example. For those that haven't seen such things before, that's a rotating black hole, and it has a spheroidal symmetry, but it's not actually charged. So it has an angular momentum, but not a charge. The Kerr-Schild field and the vector, in that case, can be written like this, so we don't really have to worry about all these definitions here, but I just wanted to define that r here is this spheroidal radius, so it's not the normal spherical radius or spherical bonus, but now in spheroidal polar coordinates. Now this parameter a has units of length, but it's actually related to the angular momentum, so that as a goes to 0, that thing reduces to Schwarzschild, as indeed it must. And in fact, you can show that the source for this thing, the minimal source that you need to get a Kerr black hole, is a thin rotating disk. So you can take a disk in the XY plane, for example, which has a certain profile of mass along the disk, and then if that's rotating, it'll set up one of these Kerr black holes. So we can then ask, what do you get if you take the gauge field, or the single copy obtained from this black hole? Well, you then, perhaps unsurprisingly, you get a rotating disk of charge. So we saw for the Schwarzschild black hole that charge gets replaced with mass in the gravity theory. This is exactly the same. And the rotating disk of charge that we get has the same charge profile in the gauge theory as the mass profile in the gravity theory. And we can do fun things like plot the magnetic fields, which most of us haven't done since the first year undergraduate or something, but we're quite excited about this. So we plotted the electric and the magnetic fields of our single copy Kerr black hole. Here the disk that is sourcing it is lying in this plane here, and then we're gradually zooming out from the disk. And indeed at large distances it looks like a bar magnet or something, and that's completely obvious when you think about it, because what a rotating disk of charge is it's a lot of coils of current. And that's a solenoid, of course, so if you zoom out, it should look indeed exactly like this. And again, there are higher dimensional generalizations of this, which are the well-known Myers-Perry black holes. So you can have more rotation directions, it gets more complicated, but essentially it all works out. So I have mentioned that there are sources for these fields, as indeed there must be, and I want to say a few more words about those. So the Schwarzschild single copy is sourced by just a point-like charge at the origin. So I can write a current density for that, which goes on the right-hand side of the Maxwell equation, and that is this amount of colour charge, some vector which is just pointing in the time direction, and a delta function to localise it at the origin. And then the gravity source, if you work it out for the Schwarzschild black hole, well, this is a known result anyway, it's just a point particle at the origin which sources the Schwarzschild black hole. What's interesting here is that this source in the gravity theory itself seems to have a double copy-like property with the source in the gauge theory. Now that's not necessarily expected. We expect the fields to double copy, but the sources are extra degrees of freedom, if you like, that we put into the theory to actually source the fields that would double copy. So it's a nice result for Schwarzschild, but we do indeed find for the Kerr black hole, things are a bit more complicated. So as I said, the source for the Kerr black hole is a rotating disk of charge, so you can write a source current for that in spheroidal coordinates, which is that the current density you need is some charge profile times just some 4 vector, which is whatever it is. And then this charge profile here, well, the delta function of z just means it's a very thin disk in the xy plane. Rho is the cylindrical coordinate, so this is indeed a disk. And this is just some profile of charge on that disk. Now, if we look at the gravity source, then we find a term which is basically double copy-like with this, so it's the same charge profile but with 2 copies of this vector. But then there is an additional term, and that actually points in the radial direction on the disk and kind of acts to stabilise the disk. Now, the basic reason why that's there is because like charges repel each other in gauge theory, but they attract each other in gravity. So if you insist on a stationary solution, you do need something else on the gravity side to stabilise the source, but that isn't necessarily on the gauge theory side. So there's still a few puzzles and mysteries about how the sources behave in this classical double copy. There is a very nice paper recently by Alex Ridgway and Mark Wise, where they look at this in more detail. So they look at extended sources with particular assumptions, and then make some arguments about whether you satisfy the energy conditions in GR and so on. So that's the simplest case we know how to do, which is this stationary Kerr-Schild type of metric. Can we go beyond that? Well, the answer is yes, we can in a number of ways. First of all, if we apply the Kerr-Schild ansatz in momentum space rather than position space, then we find that we can reproduce known amplitudes in the self-dual sector of the angles of gravity. So I mentioned this paper earlier on. We actually know quite a lot about how the double copy works in the self-dual sector. We find that paper can essentially be rewritten, or that part of the paper can be rewritten in this Kerr-Schild language. That again convinces us that this Kerr-Schild idea is somehow pivotal to the classical double copy. We can also try and generalise 2 solutions which have more than one Kerr-Schild-like term. So you can add a second term which has a second function different to this one, and a second vector, and certain mutual orthogonality properties between the 2. That form is already much more complicated than single Kerr-Schild when you plug it into the Einstein equations. It turns out that they're not guaranteed to linearise, but for some solutions, something utterly remarkable happens. There's a lot of magic, a lot of terms cancel, and indeed you get a linear solution. So one of those is tau nut, That's a solution in general relativity that has a non-trivial rotational character of the gravitational field at infinity that's been argued in the past to be a bit like a sort of gravitational analogue of the magnetic monopole. Now, if we plug this into our single copy procedure, we find that the single copy is indeed a dion, so it's something that has a electric and magnetic monopole charge in the gauge theory, and the electric charge becomes the mass in the gravity theory, the magnetic charge becomes the nut charge. So as I say, there has been an analogy proposed before between the Tauert-Nut solution and magnetic monopoles or dions. Those arguments typically rely on a large R where things are tractable and so on. Here we really have an exact relationship. So it tells you that you have two solutions in two different theories. They're exactly related by this classical double copy, and that works at all values of the coordinates and so on. Now, something else we can do is look at non-stationary solutions, because that's another restriction we made at first. There are some known cases, so for example, plane waves and shock waves that were shown before to double copy. What we've shown is that those are a special case of this Kerr-Schild picture. The time dependence from a Kerr-Schild point of view is rather trivial there, because this Kerr-Schild vector is just pointing on the light cone. So, you know, yes, they're non-stationary, but they're not that non-stationary, if you see what I mean. A more complicated example is an arbitrarily accelerating point particle. So that's perhaps the simplest, non-trivial time-dependent solution one can think of. So what one can do is take a particle moving along this arbitrary time-like world line here, and then you could look at some point x in your space and say, what is the field generated by this particle here? And if I drop a light cone so that it meets this at the point y, then the Kerr-Schild vector turns out to be that vector there pointing along the light cone, and r here is the retarded distance. Now, I will also use this vector lambda, which is just the full velocity, or the tangent to that world line. So these are the Kerr-Schild functions, and this is something that you can look up from the literature. You could then take that and construct a single copy gauge field, as we did before. But when you do this on both the gauge and the gravity sides, you find that you get non-trivial source terms on the right-hand side of the Einstein and the Maxwell equations, respectively. So I've not bothered here showing the delta function source corresponding to this world line itself. That is implicitly there. These functions are actually defined at all values of the space, and we spent some time trying to interpret, really, what these meant. I'll talk about that shortly. These sources then depend on lambda dot, which is related to the acceleration of the particle, and this rect here just means that everything's evaluated at the retarded time. So how do we interpret these source terms and what they mean? Well, first of all, we can note that the Kerr-Schild field itself is the boosted Coulomb part only. So if you actually work out what this thing represents, for example, in the gauge theory, you'll find that it's just the boosted Coulomb solution. One way to see that quickly here is that the field itself goes like 1 over r, so the field strength will go like 1 over r squared, and that's what a boosted Coulomb solution looks like. There's no radiation, for example, because that should have a field strength going like 1 over r. So that gives us the clue indeed that these sources should somehow be encoding the radiation, and indeed another clue for that is that they go like the acceleration of the particle, and it's only an accelerating particle that can radiate. Now we can actually see that explicitly as follows, that these things encode the radiation. One way to see that in the electromagnetic theory is that you can add what we call a radiated gauge field to the Kerr-Schild field A. So the Kerr-Schild field just went like kμ over r. You can add this thing to it. That thing is such that it satisfies the Maxwell equation, but with minus the current on the right-hand side, so that if you add this to the Kerr-Schild solution, you get a vacuum solution, and that vacuum solution looks like this schematically. And in fact, that is just the well-known Liénard-Richert solution. So that is the solution that we know describes a radiating particle in the electromagnetic theory, and thus that tells us that this Kerr-Schild current is encoding radiation. So the fact that we chose Kerr-Schild coordinates in the gravity theory somehow insisted that the radiation appear on the right-hand side of the equation rather than the left. And there's a similar story then for the gravity source. Now, in fact, we can use that to get a nice link to amplitudes. So again, you know, more evidence, or more convincing at least, that this classical double copy is the same as the BCJ one. I can think of the Maxwell and the Einstein equations as just consisting of acting on the fields with an inverse propagator. So I can write the Maxwell equation like this. By definition, the propagator is the inverse of the operator that acts on this field. And if I compare that to the NSZ procedure for truncating Green's functions, then that means that, well, first of all, what is this thing? that is some off-shell field at a point x, which tells me what the field is due to some particle, possibly radiating stuff to that point x. If I then truncate it with this inverse propagator, that gives me an amplitude. So it tells us that if I take these currents and I contract with polarization vectors or tensors, those must be the amplitudes for gluon or graviton emission. Now to look at that in a particular limit where we know what the answer is, we can look at the Bremsstrahlung limit, where we have a particle following some constant world line, and then it has a kink and follows another direction, so it somehow rapidly accelerates between these two fall velocities. If we do that, you can show in momentum space that these Kerr-Schild source terms have these forms here. Now, not everyone will have seen these before, but many people will have. These are the well-known icodal amplitudes for gauge theory and gravity. So these are the known amplitudes for the emission of a kind of soft radiation from a rapidly accelerating particle. So indeed, again, this tells us that this Kerr-Schild double copy is precisely equivalent to the BCJ amplitude double copy. Now, I should also mention an alternative approach. So, for want of a better term, I'll call this the Imperial College Group, although some of them have now gone their separate ways. But one can write, well, they have a very nice approach where they look at taking the linear theory, so they take a linear terms only in a gauge theory and a gravity theory, and they write a very general expression which says that arbitrary gravitons, plus two forms of dilatons that may be sitting in here, could be written as convolutions of fields in two different gauge theories. So the idea here is that if you have a product in momentum space, as in the usual BCJ story, then that would give you a convolution in position space, which is this convolution here. And phi here is some intermediary field which then sort of contracts with these two gauge fields to give you the graviton. Now they've so far used this to get a very nice complete catalogue of various theories, with and without supersymmetry, or with and without matter, for example, and really sort of show that many, many different theories obey this double copy idea. And also this statement, in principle, works in different gauges, if you also keep track of ghosts and so on. So I think it would be very interesting to see if non-linear terms can also be included in this story, and it would also be nice to look at the relation with this Kerr-Schild approach that we have. You know, if both are correct, then they really should match up with each other. So everything I've said so far in the talk is basically perturbative. So we looked at exact solutions, but those were fixed order in the coupling type solutions still, so there was still in a sense perturbative in some gauge. We might ask, can we actually go beyond that, and can we try and formulate some non-perturbative version of the double copy? Now what made all examples of the double copy special, so another way of saying it, is that they all relied on the linearized biadjoint theory. So to remind you what the field equation is for that theory, it's this thing here. And we saw in the classical double copy that the field phi, that you don't square when you take the double copy, is a solution of this linearized theory. And in the BCJ story, it's the denominators that you don't square when you go to gravity, and those again are scalar propagators, so somehow solutions of some linearized biadjoint theory. And I said that these theories were interesting because perturbative amplitudes act as building blocks of gauge theory numerators. There is the hope then that if one were to find a non-perturbative version of the double copy, you would start by finding non-perturbative solutions of this equation, and then hope that you could use those as building blocks for exact non-perturbative solutions in other theories. And this may ultimately explain the origin of the double copy. If it's really true non-perturbatively, then it's somehow a complete statement that these two theories are related to each other. So the first step in this approach is to find some non-linear solutions of the biadjoint theory. So just for fun, I shall show you some. As a first attempt to solve this theory, you might try the following factorized form. So you could say, well, let's say these two types of charge don't really talk to each other. We can factor them off in this way. You'll find if you do that, that immediately linearizes the biadjoint equation, so it doesn't actually lead to any interesting non-perturbative solutions. Somehow to get a kind of soliton-like excitation of this field, you need both charges talking to each other to kind of build the thing up. Next, you could restrict to another case which is relatively simple. So you could ask that both of these structure constants are actually the same as each other, and then I'll just define a normalization constant here, which is just how I've normalized the color generators, essentially. And if you do that, you can look for a spherically symmetric solution of this form, so a static spherically symmetric solution, and you find that there is indeed such a solution. This is spherical symmetry in the internal space, or the kind of colour space here, and it has this form. All the factors are fixed here, I should say, because this is a non-linear solution. But it goes like 1 over r squared, and it also goes like 1 over y. So I call this thing non-perturbative simply because it involves an inverse power of the coupling constant. If you were to take the coupling to 0, then this thing simply wouldn't be there because the interaction term would vanish. I can also call this perturbative about strong coupling, or non-perturbative, it's up to you. Now this thing does have a well-defined energy apart from at the origin. So the energy is perfectly well behaved at infinity. If you construct the Hamiltonian and so on and work it out, this is the energy. But the divergence at the origin is purely because you have some point-like object which is localized at the origin. So it's the classic sort of problem of infinite energy that you get in electromagnetism or something like that. If you put a cutoff in, you do get a well-behaved result. Now you can find more interesting solutions if you look at the case where both groups are SU2. You can write an ansatz then that looks like this, because you can have mixing between the colour indices and the space-like indices, and then you can put some arbitrary form factors in front of these different invariant tensors. And if you do that, you then end up with some coupled nonlinear differential equations for the form factors, where this bar notation just means I've scaled out the coupling. And then the first thing one can do is perhaps look for a pure power-like solution, and indeed there is a whole family of solutions, and they look like this. So again, they go like 1 over r squared, they go like 1 over the coupling, and it has this cylindrical symmetry now in the internal space. And k here just is some arbitrary thing going between 0 and 2, if you want the field to be real. So again, you can work out the energy, and it's well defined if you put a short distance cutoff in. As another thing to try and do, then I thought, well, what if you just imposed the cylindrical symmetry, but you looked for a non-trivial form factor in each of these terms. In fact, solutions like that do exist in Yang-Mills theory. They were constructed by Singleton some years ago. Such solutions don't exist here. So these non-perturbative solutions, perhaps unsurprisingly, of the biadjoint theory are simpler. And then we can at least start to ask, is there anything in Yang-Mills theory that could be related to these? It's not clear whether a zeroth copy relationship exists with Yang-Mills solutions, or even how to find one, and that's because what we mean by the double copy has traditionally relied on solutions of the linearized theory, which we can't rely on here. But I do note that there is an interesting resemblance between the Wu-Yang monopole and the solutions that are presented here for the biadjoint theory. So there is a gauge in which you can write the Wu-Yang monopole as 0 for the zeroth component, and then this combination here for the space-like components. And the different power-like behaviour, so this is 1 over r rather than 1 over r squared, can just be traced to the different dimensionalities of the coupling constants, the biadjoint and the scalar theories. And somewhat intriguingly, if you take one of my biadjoint solutions, then it does look like some kind of product of the gauge theory ones. So because we're in SU2 cross SU2 here, the space and the colour indices are kind of on the same footing. If you trace over these indices, it gives you something with 2 adjoint indices, which indeed could be this. Now that, of course, could simply mean nothing, but it's an interesting piece of speculation that I'll end with. So, my conclusions. The double copy is a widely studied relationship between scattering amplitudes. If it's really a property, though, of gauge theories and gravity, there should be some non-perturbative or exact manifestations of it. And what we've shown is that classical solutions do obey a related double copy. We've got a particular family of those based on stationary Kerr-Schild, but we also know some extensions to that. So we have time dependence in there for some of them, and also multi-Kerr-Schild solutions. And then I've also presented some exact solutions for this biadjoint theory with a rather optimistic hope that those could be useful in trying to find a non-perturbative analogy of the double copy. So I'd like to end perhaps with some open questions that arise from the things I've been talking about here. So first of all, can one generalise this classical double copy beyond these Kerr-Schild forms? In particular, it would be interesting to see examples where you do have a dilaton or a 2 form turned on in the gravity theory. Also, all of these Kerr-Schild things are basically linear, so it'd be interesting to see if one can find any example of a non-linear solution in Yang-Mills that copies to a gravity solution. These practical questions that I was talking about could be nice as well. Can one use the classical double copy for practical applications in either astrophysics or cosmology? Are there any other non-perturbative solutions of these biadjoint field equations? And then can they be used to get some non-perturbative double copy? In other words, relate non-perturbative solutions in Yang-Mills and with gravity. So with that, I'll leave it there. Thanks.
Questions? clock.
I think that the association that you show between gauge field solutions and gravitational solution is indeed very suggestive of BCJ and very nice. But in the beginning you had two goals. Goal one was to show this correspondence, and goal two was to directly relate it to BCJ. Because you show that if H goes like A times A, then you can get solutions on both sides. But did you directly relate it to BCJ as
So I showed a number of pieces of evidence for that. One was that what the phi field is in this Kerr-Schild approach is essentially a scalar propagator. And that is the same as the BCJ story, in that when you copy the numerators in the BCJ story, you leave the scalar propagators intact. And the second piece of evidence that I showed was, if we look at the accelerated particle, we find that this Kerr-Schild description, which is needed to get the manifest double copy to work in the classical picture, at least make it an exact solution, that then creates these interesting source terms on the right-hand side. The interpretation of those has to be that they're amplitudes in the theory, and indeed they're known amplitudes in gauge theory of gravity that double copy. So that again shows that the fact that the Kerr-Schild description has forced it to appear in that way is to get the Kerr-Schild double copy to be manifest, and then we see exactly that Kerr-Schild double copy is the same as the BCJ double copy.
So that would be some partial evidence, no?
Well, it depends what your criterion is for saying what the full amount of evidence is. I mean, it would be wrong to say that it's exactly the same as the BCJ double copy, because the BCJ double copy is for amplitudes. This is for classical solutions, but what we're saying is they're two facets of the same thing. So where they overlap, you can show that they're equivalent, but of course they're also talking about two different things.
More questions? I guess everyone is in need of coffee.
That's my fault, sorry.
All right, let's thank Chris again.